Okay, today I want to talk about negative masses. And before anything, usually it is not acceptable to put negative masses. That's the way the general consensus is, that our physics today does not allow negative masses, and whatever I'm going to say is will be uh, a reason why logically there seems to be the word is not probably inconsistency, it's just not comfortable. Yeah, it doesn't surely there is, I don't think there is an inconsistency, at least I don't see any inconsistency. It doesn't seem to be a contradiction either, but it's just not a intuitive solution. It is pretty much like speed of light being or anything moving faster than speed of light in vacuum. And again, one can imagine what might be the logical issues with that. But in principle, one might say, oh, why not? And then, yeah. So the challenges with that, logical challenges with that. So that's something, and it will come out reasonably clearly when I do that. And before I start anything, let me at least point out why should we worry about this? In what context does this come up? One is surely we have what is called dark energy, which basically means that our universe is expanding, but while it is expanding, it is also accelerating. That's not expected, right? If gravity is the most dominant player in our universe, then it doesn't make sense that our universe should be accelerating in its expansion. And that seems to suggest that there is something other than gravity, and gravity itself doesn't involve negative masses. So if there were negative masses possible, then that might solve it immediately. But as we will see, that it doesn't solve it because of the reasons. So that's one of the reasons why you would, in an immediate naive sense, think of negative mass. Second is matter, antimatter, right? So whenever we say matter, it is very clear that there is antimatter also. So if that is not a familiar idea, experimentally, it is very easy to create antimatter. So antimatter as a concept, it's not a concept, it exists. We know because in the lab we can create antimatter. But then what are the properties associated with antimatter? And then you talk about what about its mass? Is the mass negative or is it positive? And the answer is that antimatter has positive mass. That's our consensus again. But then energy, what is energy? And those are all questions you can ask yourself. And that is one place where you would think about negative mass, even though, again, I repeat that antimatter and matter have the same mass, like they don't have opposite mass. So that's one place where you would think about this. Third is, for example, if you think about the electric charge, like charges or positive charge, positive Q and positive Q, so they repel, right? Electromagnetism charges repel. In gravity, masses attract. And there is, and there is one more thing or two more things you can add to this, correct? One is currents, right? We know that like currents, so there was I1 and I2, magnetostatics, that's what I mean. So like currents attract again. So this is attraction, like magnetostatics, that's what we're talking about. And one can ask the question, what about if there was a scalar field, right? There is a question of gravitons itself, but gravitons probably is covered inside this itself. And one way to look at this is that the way we understand the interaction between these cases, is it the property of that interacting particle? Here it is photons, here it is gravitons, and if it is magnetostatics, it's again photons itself. The property, the spin of that apparently, so the understanding is that spin of the mediator means the particle that is being transferred between them in the interaction, plays a role in the sign. So the general idea is that this direction is given by that. So if you want to address those questions, which is not completely understood, it has been thought over by many people, but it is not, there is not a complete consensus there. So then you want to
What do you mean by spin of the mediator here?
Spin of photon, like if
yeah,
so there's a
they are all like
interacting.
Like they are all integral spin particles, right?
Integers, but minus, suppose it is -1 raised to s, right? So we are talking about scalar, photon, graviton, right? 0, 1, and 2. Like think of a s, so scalar. So if the, or not scalar, if the scalar, the interaction particle is a scalar, then that s is 0. If it is a photon, which is s equal to 1, and graviton is s equal to 2. So clearly you see that photon is -1 raised to s. That's -1, and graviton is s equal to 2. And then it is +1. So again, this is contained in there, and even there is good amount of literature on it.
How is the unlike charges explained with that idea?
Because photon, right? Photon is a mediator in this.
Yes, but if you put, so I get that, like it gives a negative sign for -1 raised to the power s. But if you have a plus charge and a minus charge,
mediator, I mean, this is the,
right?
I mean, you can put a minus sign in front, right? I didn't tell you what is the expression. Relatively speaking.
Okay.
Photon and graviton will change by a sign, I'm saying. Correct. So, and then the question comes, what about the current? But this is a different issue altogether. I mean, magnetostatics is only superficially magnetostatics. It's not complete magnetism. So that has other challenges. That can be covered in a graduate level. So what I'm trying to say is that these are the places where you will like to think about. And of course, eventually, there is also this inertial mass and gravitational mass. Inertial mass and gravitational mass. In all these snippets, you will at least address this in some way. It might come to your mind that, oh, what about negative mass? And often you just rule it out. I mean, it's almost immediate that, oh, no, we don't want to deal with this. And let me also, since I'm listing all this, let me also say that dark matter, right? Why not? Like, there also we have an effect which could help if there was negative mass possible. Okay, so all that is just for motivation, or not even motivate keywords when you will think about this concept. Okay, so I will here assume that there is negative mass and pretty much use Newton's laws and pretty much replace m with a negative number and see what are the consequences. And let's see what it is. Why is so? or at least one reason why it is not comfortable. So let's let's write Newton's laws. So Newton's law says that mass times let's say this is mass times acceleration. So this is second derivative of a position. Right? This is the system is m1 at this point. R1 is its position and its motion, not including velocity. Its acceleration is the important thing. So Newton says that the motion of m1 is equal to the sum of forces acting on it, vector sum of the forces acting on it. But let's say there is only one force acting on it. So that's your 1 and that's 2. And this is on 1. So let's say this is we are talking about gravity, right? So, or let's talk about gravity, because then both this gravitational mass also comes in. So let's say this is force on 1 by 2. So this means on 1 by 2. So, and let us also say that that's gravitational force. So instead of saying, so remember that we would say it is G m1 m2 over r square, right? So instead of that, I'm going to write that. So I need the direction should be r2 minus r1. So I'll say this is minus of r1 minus r2. So that's a complete. And then r1 minus r2 cube. So that's Newton's law of gravitation. And we already see there is m1 here and there is m1 there. So just for convenience, just to differentiate between them, I'm going to write this as q1 q2. That seems like we're talking about charges, but no, these are masses. Okay, that's just to differentiate. So this is m1 here is what is defined as inertial mass. Okay. And m1 is moving, so it is moving because of, so q1 is what is moving. So this is what will be called the active gravitational mass, because this is what is getting affected, right? Gravitational mass. Hopefully I got that right, active and passive. And there is another mass that is creating it, right? It is q2. As far as m1 is concerned, q2 is creating the field and q1 m1 is moving under that. So q2 will be passive gravitational mass. Okay.
Could you distinguish between the inertial and gravitational mass, or you're going to talk about it?
It is just how it appears in your equation. Notice in Newton's laws, this is a force, right? This is the identity of the particle. This is the one that is moving, especially when you go to general relativity. This becomes geometry, correct? In fact, m1 doesn't even appear, right? In general relativity, you would say that m1 is equal to q1. That's necessary. That's a starting point. You would say that a gravitational mass is equal to inertial mass. That's equivalence principle, Einstein's equivalence principle. So that doesn't even exist. And then the geometry is taking care of this whole thing. That's how you would proceed. But I'm saying, and there is no need to put this q1 and q2. I can cancel it out. But what I'm going to show is that, first of all, I'll make it very simple in the analysis here. But in principle, you can carry it over. And this whole thing just stays as a product. It doesn't really matter. Right? It is mostly the definition of inertial mass that will be important. Because whatever is positive and negative, this is just going to change the overall sign in there. That's my point. But that's just for pointing out. So as it's just for bringing that out, I'll write two equations and immediately make it simple about that. I'm just keeping this general just to bring out that, okay, I'm not, this is really serious, the matter. It's not because of the simplification that something happens. So let me write the second equation also, M2. So that's could also be a system. What happens to the second equation? So that's equal to this will be minus again, right? So G Q1 Q2 R2 minus R1 over R1 minus R2 Q. So that should be straightforward, and so this is your 2, 1, right? And for consistency, it is also possible that you would like the whole system to be, or there's a third possibility that you treat 1 and 2 as a single system. And then again, why did Newton introduce the third law? I would say it is for the consistency that you don't expect it to move. If there is no external force, it should not move. So these two should cancel out. If you add them, that should behave like there is a single point and it should not have any motion. And we will see exactly that will happen if it is a negative mass. Just because of nothing, it will just start moving on its own as a whole. So now let me make it simple, right? So I'm going to, so this is where I introduced negative mass. So let's say this is just for simplicity in the just to bring out the idea. So this is for simplicity alone. It goes through even if you keep it more general. There are more possibilities that are. So let's say Q1 is equal to M1. So M1 is equal to, so Q1, that means to say that inertial mass is the same as gravitational mass, and M2 is equal to Q2. That means whatever happens to gravitational mass happens to inertial mass also. And the
second equation, you meant to write R2 on the left hand side, right? R2.
Oh,
second
yes.
equation.
Yes, sorry. Yeah. Thank you. Yeah, so that's the position of the second part. Yes, with respect to some origin, right? Yeah. Nice. And we say that, let's say M2 is equal to, so this is the catch. So now I'm saying M2 is negative of M1. Let's say M1 is positive and M2 then is relatively speaking negative, or if one of them
help again. So what are you doing now? Why M2 is equal to negative M1?
That's the negative mass.
Yeah, but why M2? Make, if you want to change, you change the mass M1 itself to negative mass. Why are you changing the second mass?
If you want, why is M1 any special?
No, I don't get the point. Like, the point is there is an interaction of two positive masses. Now you want to introduce an interaction of another negative mass. You never said that M1 was equal to M2, right? You didn't say that M1 was equal to M2.
Oh, I am going to, okay, so maybe let's first say, how about this? First, let's do M1 is equal to M2. That's again for simplicity alone. You can keep this, it's just that it brings it three conditions then. Oh, this can happen, that can happen. There are more conditions, but my idea is to bring in one non-trivial issue. And if this is acceptable, and let's also say why create 1 and 2 just as plus M. There's only one mass, right? And one of them is negative, right? So now I want to put that negative sign, and that's what you're not allowing me. So how do you?
I don't.
Okay, how about this?
Why don't you finish your equation first with M1 equal to M2? Write an equation for M1 equal to M2, and then you can say that one of the mass is negative.
Okay.
Or it doesn't work that way.
I mean, it works, but it will be two more equations writing. It will be just copying it down again.
Okay.
Right. So
right.
Just saving space, I guess. So let me say that, how about this? M1 is equal to M. Maybe this is better, plus M. How about that? So if you want, if this is very clear, plus M, and M is greater than 0, right? And M2 is equal to minus M, right? M is greater than 0. Okay, is that, hopefully that's readable? Okay. And let's write that equation down. And it is clear that if these are forces are acting along a line, motion is going to be along a line. And let's also say initial velocity of both is 0. So initial velocity v1 at time t equal to 0 is 0. v2 at time t equal to 0 is equal to 0. And everything is happening along one line. That's all that will happen, that much. Again, simplicity, you can start with more complicated initial velocities, just keep it simple. So I can replace all the R1s with just one variable x1 and all R2 with x2. Again, you can keep this as it is, and it pretty much goes through. If if you're not familiar with vectors, it might be more overwhelming, or there might be more clutter associated with it. That's the only difference. It just goes through. We can define center of mass variable and so on. It's primarily, the idea is that whatever I said before, there is one system here, the second system here, and the whole system, there is no force acting, it should not move. And what I'm going to show is that if you put in a negative mass, this will move. This has a whole system will move. Even though the forces are internal, this whole system will move to the right. And that's not convenient, right? Remember again that if Newton's third law did not work, these two will not cancel. So now if you notice on the right side, these two cancel. Okay? This is of the opposite sign. These two cancel, and there is a convenience there that, oh, there is no force, total force is 0. But if you can immediately see that, oh, if Q1, Q2 is opposite, then when you add these two equations, they do not cancel. And that's the basic idea. Right? The crux of the argument is that Newton's third law, the way it works.
Yeah, but Shajesh, the left-hand side will also cancel, right?
Okay, let me show it. Okay, that's the crux. I said I shouldn't have revealed it. So then it's not clear. So let me show it. So, but basic is that, yeah. Okay, so let me write that equation down. So M1 is M, right? So it is M times D2. So I had a straight line. That is M1 here. That is M2 here. That's X1. That's X2. Right? That's a position. Right? So D2 X1 over dt squared is equal to minus G M times M, right? But the other one is negative mass, notice. So this becomes plus, right? It was minus, but now it has become plus, and this is x1 minus x2 divided by.
There is another mass. You have to write the other mass.
Oh, yeah, I have to write the
M.
other ones. Yeah, let me write that clearly better. So let me write it so that it's better. So it was G M, and now there is minus M. Better. And this is x1 minus x2 divided by, right, x1 minus x2 divided by x1 minus x2 magnitude q. Better? I think that's correct. Do the same thing the other way now, but this one is minus M, right? So this is minus M. The 2 was minus M, so this is d2 x2 over dt squared. That's equal to minus G. This is minus M if you want. That's M, and this one will be x2 minus x1 over x1 minus x2. Good. I think that's right. Okay. So just to it is again copying, but I think in this case it is worth writing it down to avoid any confusion. That this is plus now, plus G m x1 minus x2 over x1 minus x2 cubed. And so this is just rewriting. So negative, that becomes negative. So this is d2 x2 over dt squared. It's equal to minus g m. Let me write it as x1. So it is plus x1 minus x2. Okay. Is that clear? You need to have confidence in that equation. Yeah.
Yeah.
Okay. If that is the case, you just subtract them, right? If this is true, subtract these equations and immediately right side is 0. Right? So second derivative of x1 minus x2 is equal to 0.
Yeah. And what does it say? Like,
yeah, so let's see what it should say. So if something is 0, that means it's a constant. So this implies that v1 minus v2 is equal to a constant. Right? But I chose, it is not necessary, but I chose, I just need to show one critical example, right? So let's choose the initial velocity to be 0. That means the constant is 0. Correct? So, so v1 equal to, so v1 0.
You are choosing v1 0 equal to 0 and v2 0.
v2 0 equal to 0. You could have chosen difference also to be 0, but there are various possibilities. I'm just saying. Initial velocity is equal to 0 implies the constant is 0. Right? That implies the constant is 0. Right? This constant is 0. That means to say that x1, so eventually you said that x1 minus x2 is equal to a constant. And let me call that a. Right? So if you have a negative mass, what you're saying is that the distance between these two particles, right, this a, for this particular initial condition will remain the same. If the initial velocity was not 0, this might increase with time. But if if it starts from rest, the distance between them will not change. Is that clear? That's the first conclusion.
Yeah, and so yeah, I mean, I'll let you finish the comment. So yeah, I get it.
Yeah, I mean, that's the first comment. That's the first conclusion, right? The distance between them, that does not change. That's still
which probably is okay,
that's
right?
probably okay. That's not as bad as that's not bad at all. That's okay. Okay, with me, Tala?
Yeah.
Okay, if that is the case, right? If this is true, that also means that this is now equal to a constant, right? So it is gm over a square, right? And it is the same constant that's coming here, gm over a square. And that's a problem, right? Acceleration is equal to a constant. We know that's the solution for that. That's the introductory physics. First thing we do, uniform acceleration motion, right? That's parabolic. It is going to grow quadratically in time, right? And since its velocity, initial velocity is 0, immediately.
Now you're talking about individual particles.
Now we're talking individual particles. This is constant. The distance between them stays constant. But if that is constant, my right-hand side is constant, right? x1 minus x2.
Yeah, no, I get it. So yeah, that is fine. That is perfectly okay.
Yeah.
Then you are just saying that acceleration is constant, which means it should have a parabolic trajectory.
Both of them will move
with respect to time.
both
Yeah,
of them
both-
will move to the right. Right? So the solution here is, so if you
they
allow
can
me-
move to the right, no problem.
well, yeah, if that's what I'm saying, there is no contradiction, nothing is inconsistent, but there is no force. What is the acceleration of the system? That's,
No,
yeah,
there
if
is
you're-
a there is a force. No, the deal
Okay,
here is that what are you calling as a system first?
sure.
Like, what is your system? The system is individual particle or system is both together?
Either way, that's my choice. That's an observer's choice.
Yeah,
That's a
so this
physicist's
is
choice.
so why are you saying there is no force? If it is individual particle, the individual particle is experiencing a force.
Okay, if you're good with, okay, so this whole thing, right? There is no force. Correct?
Yeah, but when you combine both of them together, where is the force?
Well, it is moving, accelerating. The whole system is accelerating to the right.
But I thought you showed that when you
Okay,
subtract it
Let,
out,
let-
there
let me
is
write
no.
that down. Okay, that's what I'm saying. There is no inconsistency here. Logically, there is nothing inconsistent. If you're comfortable with that solution, go ahead and accept it. I'm not comfortable with that solution, and there's nothing wrong in this. See, the way you are, like what you are trying to argue here probably is that this is a positive charge, so this is positive, right? And that's negative, right? Positive charge attracts everyone, so, and a negative charge repels everyone, so it is repelling. Positive charge is trailing it. So technically everything is logically
Okay,
correct.
let us try to do something here if we are open to it. So ideally, you should be analyzing when you define a complete system, you should be analyzing the center of mass motion, which means that you are supposed to be adding the two equations together.
Center of mass is R1 minus R2 here. So that's the challenge because it's negative. This is center of mass. X1 minus X2 is the center of mass. The center of mass is moving.
Now I'm confused actually.
Let's remember center of mass, right? M1 R1. So shall I write here? Yeah, let's start.
Yeah, M1 X1 plus M2 X2.
Yeah.
Like, let's do just one dimension. Why are you going in 3 dimensions?
Yeah. So, like, you want to keep the M1 plus M2 to the left so that that issue is not there. But like I can do this better if you keep the full vector equation. I can keep that. But let me, before that, let just for completeness, right? If you want, we can do that in a minute. Okay, I can do that. But here, just for completeness, since initial velocity is 0, this immediately implies that x1, right, is equal to gm half gm over a square t square and plus a constant, I suppose, right? Plus a constant c1 and x2 is equal to half gm over a square t square plus c2, with the idea that c1 minus c2 is a, right? The distance between them is equal to a. And this is typically said in literature, they call it runaway solution. That means the two charges are running away, right, for no reason. Okay, so that's the basic basic weirdness with the negative mass. Not necessarily wrong, but weirdness, or at least we are not used to it. So now, Prachi, you're suggesting that we do this complete vectorial, correct? Agreed?
No, I don't want it vectorially.
Or
I'm just
vectorially, or using the center of mass coordinates.
like analysis of the center of mass.
Yeah,
First of all, like when I
Yeah.
raise the question, I am now thinking, what do you mean by center of mass for a
Yeah, exactly.
sum of positive and negative mass?
Yes, so I did this for the whole thing and it doesn't change anything. So
and I do not think that there is a inconsistency with that x1 going parabolically and x2 going parabolically, provided they keep their distance fixed. Because that's the solution from the bottom line is.
Yeah, if that is acceptable, that's my point. That see again, what's the solution here? X1, x2 remains the same. No force acting on the whole system except that there is a negative. They move to the right. If that is not weird, then that's okay. That's perfectly fine. So then, yeah. So that's the only weirdness in this. That's a key part. Rest everything you can accept, I think.
Okay, I think what you're trying to say here is that it is violating Newton's first law.
Not really. See, it's negative.
Yeah, because this is the idea, right? Newton's first law tells you that if it was at rest or if it was moving with constant velocity, it will continue to do so. If they were moving with constant velocity, then probably it was okay. But they are not moving to begin with. That is what you want to say?
No, but there is a force acting, right? So that's
like force is acting on the entire. Force is acting for the entire system. You are saying that there is no force acting.
Oh yeah, in that sense. But
I believe that maybe there is the inconsistency there, because for the entire system there is a force acting. For the entire system, like one force was going in F12 was going to the right, but when you flip the mass.
No, right? No. See, that is because you're assuming that the action reaction forces are equal and opposite, but now they are not equal and opposite. And on M1, this is positive, right? So on M1, this is positive, correct? This is the force. And on M2, leave that alone, that's also positive. Right? M1 is getting attracted to M2, but M2
what
is
with x1 minus x2 and x2 minus x1 part?
What?
Like you have x1 minus x2, you have to take everything into account, right?
No, I just took the right side. See, Newton's third law, this is the force on 1/2, the arrow, right? That's to the right. Intuitively, our normal physics tells that gravitation force are equal and opposite, third law. But now the
Shajesh, I think I'm getting confused. It's really getting confused, please. So can you please take your origin is somewhere, okay? You have a sense of x1 minus x2 and x2 minus x1 also there.
There is no origin, right? X1 minus x2, that's relative.
Yeah, right? So when you say x1 minus x2, that quantity will be either positive or negative. Something will be there, right? Depending on
so you want, you're saying that, x1 minus x2, the way here it is negative. Okay, flip that. But then the other one will also flip. Correct? I'm saying relatively speaking. Like, fix this quantity, right? This is not the important point here, right? This is positive. Suppose this is positive, that's negative because that negative sign has to go away, right? That negative. Right, so it's acceleration, the force is to the right. Correct?
Okay.
So I'm saying the action reaction forces are in the same direction, so it will move to the, so Newton's first law is saved that way. So there are two forces.
But then where is the inconsistency? If you're saying there is a net force on the entire system, you're saying that there is a net force from a stationary observer, there is a net force acting, then it is accelerating. What's wrong with that?
So I think I started.
The only thing you are proposing is that the distance should always, like relative distance should always remain a constant. That's all you're proposing.
A disclaimer here, right? I think the title that I sent should not say inconsistency. Like initial weirdness, maybe it is weird, that's all. But there is no inconsistency. This is a runaway solution, like there are two particles, just because there is repulsion, they start moving to the right. Yeah, it's just not We are not used to that intuition. Maybe if tomorrow, if you show us an experiment that does this.
So are you trying to say that there is an inconsistency in the sense of action-reaction pair, like third law?
No, there is no inconsistency in Newton's law, because if there was an inconsistency, then you say that this is impossible.
Okay, Shajesh, like one of the laws has to be violated, right? You
I'm
are saying that the first law
violated.
is not violated, but then action-reaction pair is not acting in this equal and opposite direction, like they are not having opposite direction.
It is opposite in the sense of this mass flipping, right? So the mass has this feature in it, correct? So yeah, I mean, the way we say it, it is not true, but I'm saying mathematically it is okay because there is a negative sign in it. It's taken care of. So yeah, with that negative sign in picture, it is okay. It's consistent, I'm saying. We say typically that, yeah, action is always in the opposite direction to the reaction. That way it is, but that's not inconsistent, I'm saying, because the negative sign is what's playing the role there. Does that make sense? The way I'm saying?
Yeah. Where are you, by the way? You're not in the frame.
Oh, I'm on the right or left. Okay. Yeah. So, yeah. So, yeah. So, yeah, in principle, the idea is can wait, and that's all that. And the best I can say is that I can do this using center of mass coordinates, keep it slightly more general. I can make this inertial mass as a gravitational mass
Center of
different.
mass, like I don't know how you will define the center of mass in this case.
Again, we everything keep the same. M1 R1 plus, or I don't have to define it, right? I just start from these two equations, the vector equations there, right? So
like don't go R1 is not necessary, you can still do it in one dimension.
yeah,
like you can define center of mass in one dimension.
Why not keep the whole thing? There's nothing lost or gained. So I have done the simple case, conveyed it. Now keep it very general, keep even the Q1 Q2 in there, just add these two equations, same idea. Add these two equations, this goes to 0, right? And you have M1 R1 plus M2 R2 sitting there. Put
yeah,
M1,
but if you put M1 equal to M and M2 equal to minus M, if you add those two equations, the left hand side will give you a I don't know what it will give.
same thing. R1 minus R2 is a constant. Right? Same thing goes through.
Yeah, but that is not defining your center of mass, right?
Oh.
How will you define your center of mass?
Okay, you can do this in next step. Keep them M1 and M2 the positive. Define your center of mass, right? Then you will get two equations. I can immediately do this instead of talking. Right, so that if you have two equations, or so I'm no positive and negative at this point, right? So R1 plus M2 R2, right? So this is M1 plus M2. I'm writing it on the left so that it doesn't seem like it is in the denominator, that's all. And but it doesn't, that doesn't seem to be the issue. So R1 minus R2, right? And you immediately
capital R or small r? Okay.
Capital R. This is capital R, that's small r. R1 and R2 are the actual positions. Right? This is the position between relative position. That's the center of mass. That's a classical concept, right? So again, no negative masses here. So this equation will become immediately. So second derivative of t squared will of M1 plus M2 times R. Right? That will be equal to 0. which you can see by adding these two equations, right? The second will be second derivative d by dt square of, remember, the reduced mass comes in, which I will keep it on to the left, right? So I think so. So yeah, so this is R, that's equal to everything stays as it is, so it is minus G Q1 Q2, that's vector R now over RQ, correct? And one is M1 over M1 plus 1 over M2. And usually this is called the reduced mass, right? So reduced mass is 1 over mu is equal to 1 over M1 plus 1 over M2. So if this was 1 over mu, you take it on this side and say that is the equation of motion typically. But now you again say, okay, now the main point that happens in the special case we are doing, if M1 was equal to M, which is greater than 0, and M2 was equal to minus M, both these equations are the same. They're identical, right? Because this goes to 0 now. M1 is equal to M2. That goes to 0. And this is the same equation. This becomes, capital R becomes smaller. So the coordinates are becoming identical. Like the two coordinates become a single coordinate. There is no independent equations there. Like this should clearly give you what is happening. Like this goes to 0. And R goes to R. Like in this implies that R goes to R. And again, the whole thing happens, repeats itself.
I don't know. It bothers me to think in terms of the center of mass of a positive and negative mass. Like you're saying that capital R goes to R, but I cannot see it from the definition itself.
Oh, this one minus. No?
Yeah, but left hand side M minus M is 0, right?
Yeah. Yes, exactly. Yeah, maybe. Or maybe you don't want to say that center of mass goes to 0. This equation will become identical to this. Maybe that's the way to look at it. Like, let's not define center of mass, right? That's just a convenient substitution you made when you were doing normal mechanics. But here you will get the same equation. I'm saying you won't be able to escape that, or that is, at least I don't see any. Is there some special case you can do some infinity or something that is a non-trivial solution there? I cannot see it. Yeah, exactly. Like if this, like the way I was looking at it, oh, if this is 0, that means, oh, center of mass need not be 0. But that was just a convenient substitution. The right side is the important one. And that is all there is. Like when I add these two equations, I'm just doing this plus this. That was a coordinate substitution. So if right side is 0, that's, or right side is R1 minus R2, it is the same variable as this. maybe that's what we want to see, that there are two coordinates needed for this motion, but both the coordinates are becoming identical. So somehow the way you would look at it is that it's a space of two variables, and there is a region of space where that is becoming identical. It's basically 1 degree of freedom is getting lost, right? So then, somewhere that metric or like space is decided by the metric, right? If you lose one of the directions, somehow you're not learning anything about that direction. So maybe that gives some insight into what could be happening, right? That this is getting identical to this, so maybe you have to introduce such a variable that doesn't go to 0.
Okay, can we also analyze the gravitational force direction again using Q1, Q2?
Yeah, but my point here is that on the right side, whatever I do with Q1 and Q2, these two are the same, right? So, but instead of overall repulsion, it might become overall.
I understand, but in the first case, like I'm talking about the Newton's third law again. So whatever you do to Q1 and Q2, that GQ1, Q2 factor will remain the same in both the forces.
Correct.
But your R1 minus R2 and R2 minus R1 will still change the sign.
Correct.
Which means that they should be equal and opposite.
Yeah, they are equal and opposite. Yes. Yeah. But yeah, I think that's the point. Like, why do we have that relation when we add those two? In this case, you will subtract. No, add, right? Because this is different. So when you add those two, on the left-hand side, whatever comes should be consistent. That's all we are saying, right? Earlier, we would have wanted there to be no motion, correct? And this time there is this negative. Yeah, I think the point is that negative sign, do you want to move it to the right side or not? I think that's the way to look at it. Yeah, you're correct that I see your point that, if you look at between these two forces, they're equal and opposite. But there is a new negative sign that has come. And do you want to talk in terms of acceleration or with that, momentum, rate of change of momentum? If you talk in terms of acceleration, then the negative sign moves to the right. But if you talk in terms of rate of change of momentum, then the negative mass stays to the left. But in my understanding, that's consistent. That's my point.
Like it felt like when you were drawing the forces on the other side that there is a net force acting on the system when mass changed. But I don't think the net force on the system has both positive directions. Like it is having this.
I think what I'm drawing there is let's say acceleration. Yeah. So acceleration is force with the mass, right? This is an action and there is a response. That's the response, right? Usually they are in the same direction because M2 is positive. But if M2 is negative, you want to say that the response is including that negative sign, right? So you would say M2 is pulling you or M1 is pushing you, but acceleration and the force are always in the right direction. Or another way of putting it is that, this is I haven't investigated this. Suppose you have a collision, right? I think this is something I read. It makes sense. Like if you have M1 coming and colliding with M2, right? Let's say this is at rest, right? So this comes with velocity v and it collides, and the general motion is that 2 will go to the right and let's say 1 comes to the rest, correct? But here what will happen is that let's not talk about equal. Like in this case, if M2 is negative, 1 will go to the left and 2 can also go to the left. So you come and collide and both will start moving to the left. So that's more associated with the negative mass. I haven't looked into that, so this just is out there. If you look up, these are the examples that show. But I think the main issue is with the gravitation. Like without that, I think that might be less of a big deal. And another point I should point out here is that one of the main reasons why you don't want negative mass is also that quantum field theory deals with the vacuum, and you don't want any energy to be below that vacuum energy. So that's and there are a lot of arguments based on that, like on a logical level you build it. But it seems like all that is a you want your system to work. That's my point. Like at a very basic level, probably in some approximation, at least Newton's law has to be valid, and then this all should come out. Yeah, so let me stop here, I suppose.